Okay, hi everyone. I think we can all agree that binaries are awesome. They are really helpful when we're trying to address different observational puzzles in the galactic center and in galactic nuclei in general. And in this talk, I'm going to focus on how binaries helping us understand the G2-like objects, the young stars, black hole mergers, and how they really confusing us when we're trying to understand the stellar disk properties. But the first question that we need to ask ourselves is, why even talk about binaries? Are there binaries in the galactic center? Do we expect binaries in the galactic center and galactic nuclei at all? We heard a lot about binaries. This is a valid question to ask. We know that in the disk, most of the stars born in binaries. And here we see the fraction of stars with companions as a function of spectral type. And our sun had a 50-50 chance to be in a binary configuration. And the more massive stars, those stars that we see a lot in the galactic center, the majority of these stars are in binaries or higher multiples. Okay, but we don't know if stellar formation in the galactic center takes place exactly like in the field. Luckily for us, so far we've observed three binaries, and we can have some estimations that the binary fraction in these in the galactic center can be comparable to those in stellar clusters or even higher. And I know that Goncia is going to talk about a little bit about eclipsing binaries, and we heard about SO2 being a binary from Andrea before. All right, so basically we have this observational evidence. We also have some observational fingerprints of binaries. We have X-ray binaries. So if there are X-ray binaries, they have to be in binaries. Okay, I'm the only one who finds it hilarious. And we have hypervelocity stars that started, the leading mechanism for them is that they started out as a binary and got disrupted in the supermassive black hole. So I'm combining all these evidence together. And in fact, Dr. Seuss said it way better than me. Binaries are here and there. Binaries are everywhere. This is exactly what it said there in the book. Okay, so let's try to understand what happens to these binaries in galactic nuclei or in the galactic center. So they experience very extreme conditions. They have extreme gravity due to the supermassive black hole, and they move around in an extremely dense environment. All of this, we're giving these binaries these X games, but instead of this beautiful beautiful image, we have another beautiful image where they move. So here we have the supermassive black hole here, and we have our binary here, and they're moving around. And I'll put this binary far enough so we're not breaking them up when they're getting close to the supermassive black hole. So no Hill mechanism here. All right, so now what we want to understand is what's going on to this binary? What does it experience? How to evaluate what's going on? So the first thing that I can say about this binary is that it's not playing very well with others. It has lots of trouble. When every time that there is one star flying by, it perturbs it and changes the orbital parameters of this binary. Also, if there is a star flying by and too close, it can disrupt this. So it can disrupt the binary completely. So close-in, this is very accurate simulation here. So close encounters or many times flybys can, at the end of the day, lead to breakup of the binary. So I'm going to fold all this beautiful and interesting physics into one timescale, the evaporation timescale. And this timescale will tell me how long a binary can live by itself like that without any other mechanisms, but flybys or any other triple interactions from stars far away. All right, what else I can say about this binary? Well, I can say that it's very sensitive. It's general relativity from the supermassive black hole can process the orbit. And if I have some mass distribution around the supermassive black hole, it can also cause a precession. We're going to hear from Jihad Tuma about resonant relaxation tomorrow. And we heard from Fabio. Where are you, Fabio? we heard from Fabio about what happened if the stellar distribution is triaxial. So it's very, very sensitive to its environment, our binary. Another thing, I would say that it's a little bit eccentric. Even if it didn't start eccentric, it started circular, on a circular orbit, it will actually become eccentric due to gravitational perturbation from the supermassive black hole. And it's trading eccentricity for inclination. Now, if you've never heard me talk about this, which I'm describing now, it's the quasi-Lidov mechanism, I'll be very happy to talk with you in length over the break, or give me an hour or two, and I will talk about this. But to make a long story short, we're talking about the eccentric quasi-Lidov mechanism, where by now we know that this conservation law, the quasi-constant of motion, is only correct if only correct to the lowest order of approximation if that valid. So it valid in a case where my outer potential is axisymmetric, for example, if the outer orbit is circular, and only if one of the particles on one of the binary members is a test particle, so no mass. Only then this conservation law valid. So we expand the approximation to the next order of approximation, the octuple, and I think that Cliff is going to talk about higher orders later. And we allow basically to both the magnitude and orientation to change. And that means that we can tap to much larger parts of the parameter space. So we no longer committed to these 90 degrees that everyone talked about. We can tap to almost everywhere. And we have a behavior which is much richer and interesting than thought of before. So just for an example, this I'm showing here an example in the galactic center. This is an inclination. This is eccentricity as 1 minus e, because we care about the pericenter passage as a function of time. And you can see here the oscillation. This is the eccentric quasi-Lidov mechanism that flips the orbit and the very high eccentricity peaks. Just to make the point, if you use the 60s calculation, the nominal test particle quadrupole, you get the blue curve, which is qualitatively different. All right, so now let's think about these eccentricity peaks. This is extremely high eccentricity peaks. What happens then? Well, in one hand, if I have high eccentricity peak, tides can work to shrink and circularize the binary orbit, because the binaries spend a lot of time around each other. So here again, inclination, separation as a function of time. And if you focus on the red, you can see in this example that it shrank. But sometimes eccentricity peaks can take place on much shorter time scales, so the tides do not work or don't have enough time to respond. And I can get a very similar plot. Here's inclination, separation, time. And I can get to the eccentricity, or the pericenter will be so large that the stars will cross each other's orbit. So now let's put our binary in the galactic center and try to see what's going on. So this is a work that was led by my student from UCLA, Alexander Stefan. We included, of course, the EKL, general relativity, tides, and then there was post-main sequence stellar evolution, the evaporation timescale, and disruption if such thing happens, and it happened a little bit. And basically, this illustrates what is happening, but we found that there are three kind of channels. The first channel is just high eccentricity spike that crosses the, that lead to a cross of the Roche limit, just like in this cartoon and in this plot. So here I'm showing inclination, separation, and this is time. And we can see here this is the Roche limit, and it crossed, the binary crossed each other Roche limit. So we call this merger. Of course, we don't know if it really merged, right? They just crossed. We have currently, we're working on this to try to understand exactly what happened. But one can assume that after a very messy behavior and dynamics, they will completely merge. But it's still a work that we're trying to understand. This is one channel. Another channel, oh, I had this funky animation here. Another channel is the shrinking of the orbit. So here we have an orbit that shrank due to tides, and we got a tidally locked orbit. And then the stars inflate due to post-main sequence stellar evolution, and basically we get a merger. And this is the more nominal merger that usually people who talk about binary evolution talk about. The last one is that we had a binary just moving around in the galactic center. No very tiny oscillations due to the eccentric quasi-Lidov mechanism. But then the stellar evolution kicked in, and again we had a crossing of the Roche limit. And this is, again, another merger candidate. So Alexander ran a Monte Carlo, and this is the plot that you guys have saw so far. So this is the fraction as a function of time. In red, I'm plotting the merger rate. In blue is the binaries. And in red is the evaporation due to interaction with single stars outside. The first thing that we can see here, that there is a rise. These are the EKL mergers, those that happen with high eccentricity spikes. And then we also have some binaries that shrank and became and came to be on a very short orbit, but they have not merged yet. They just stay there and wait until stellar evolution come to play, which is here, and they started merging. And also those whitish binaries that didn't quite had enough eccentricity to tightly lock them, but they were in the right regime, also merged here. So this is what we see here. And then a possible interpretation is that these guys here are the G2-like object that we heard about quite a bit. So again, as I said, this process is kind of messy. Imagine two stars coming to one another on a very high eccentricity orbit. We know if we just run BSC, a stellar evolution model of binaries, start on a circular orbit and let it run, it takes about a million years, few million years, for it to, after they met in Roche limit crossing, to become a new star. So this process is long for circular orbits. Who knows exactly what's the time scale for eccentric orbits, but we might think that to use that time scale as a guide. So
check whether they will be ejected beforehand by three-body interaction?
Yeah, this is what I said. This is the evaporation time scale. Everything, there is a competition. So Jerry says, what about the evaporation time scale? There is a competition. We're on the clock. We have to merge before the three-body interactions from passing stars will eject us. This is our limiting case all the time. All right, and what happened with these guys here? Well, we say, you know what? These guys, and also these guys here, after a long time, they look brand new. They, in fact, this is the ultimate facelift, right? They merge together. No one laughs for my jokes. Right, it's okay. Probably they're not funny. So they merged together, they rejuvenated their hydrogen, and they look young. So maybe these are the young stars there in the galactic center. But I want to emphasize that no matter what is your interpretation here, these things have to be there. These merger products have to be in the galactic center if we have binaries. So if Dr. says that there are binaries, they have to be binaries, and therefore these merger products have to be there. So this is this point, but then we can ask, what else can I do? Right? I had this very big guy, it's the supermassive black hole here, and I basically told it to smash. Right? So it can smash also black holes. Yes?
Could you go back?
Yes, I can.
The ratio between the green and the red curve must depend on the orbits.
Yes.
And if they spend some time in very eccentric orbits going very close to the center,
To this.
the evaporation will be low again.
So you're asking to the center of the supermassive black hole? Or
Towards the center of the cluster of stars that they're in.
so that's so let me talk.
Include the diffusion and angular momentum.
So what I do is this is from the supermassive black hole all the way to 0.1 parsec. So these are kind of closest places, and I calculate the evaporation timescale taking directly from Bini and Tremaine book, and from there we calculate just the timescale, and we use that as our limit, as a limit for the integration. So this is exactly what we're doing. What?
You're thinking of the region as one box with its properties, basically.
Exactly. That's it. This is all we do.
What are you assuming for the semi-major axis distribution of the binaries?
The inner binaries or the inner binaries? Let me see if I remember correctly. In this case, we may have taken them to Duque and Mayor. These were saltpeter. So this is a saltpeter mass distribution, and we used Duque and Mayor distribution for it. And then we actually asked, after we had Duque and Mayor, we asked how many actually are stable for long-term evolution, because I want to be able to use my approximation. So this is our epsilon, and I can talk about stability a little bit later. And also we used the Mardelin criteria, and we rejected everything that did not agree with this criteria. So we were left with less binaries than starting with. So while here it's 1, this is an excellent point, where here it's 1, the actual number may be a little bit lower. But since we don't know exactly how binaries distribute to begin with in the galactic center, this is how we started. Yes?
So let me just ask my question very clearly. Take a given binary at a given energy in a given place. But over time, its eccentricity varies. It's diffusing in eccentricity space.
That's
So
true.
sometimes it's in a very eccentric orbit. Sometimes it's in a more
That
radial
takes longer than the evaporation timescale here.
But
It takes longer.
when it's in an eccentric orbit, then it goes close to the center where the density is very high, and it's more likely to evaporate. Do you allow for this? That might change the ratio.
No, we use so the quick answer is no, because we just use the semi-major axis. This is an excellent point. Remember when I said that there are all this physics that I'm folding? It's folded and it's not been included, and this is an excellent point for a follow-up. This has not been included here. This is excellent. Yes.
The sign of it surely is to increase the ratio of the green to the red.
Yes. But I will continue now, because and we can talk about this offline. Yeah, you understood, and this is an excellent point. Not only you understood, it's a great point. All right, so I said that we're going to use the Hawk to merge supermassive black to merge stellar black holes, and we just heard Bense talk about this quite a bit. This is a work that was led by another student of mine, another grad student of mine in UCLA, Baumann Hang. And we added all of this, including Newtonian precession, and you can ask me at the end what the results was from there. This is just an example, and we looked only on soft binaries. So these are much softer than the binaries that you've heard before from Fabio. This is inclination, eccentricity, separation, just to show an example. And here, again, there is the same competition that Jerry asked about before. Things will break up due to triple body interactions, or if there is no eccentric quasi-Lidov mechanism, they might just sit there and merge. Eccentric quasi-Lidov mechanism can basically enhance this merger. And this is exactly what we get. We get two populations. One population where it was insensitive to the EKL mechanism and just sat there and won against the evaporation timescale. And this is this population. And another population here that was very sensitive to the EKL and merged quickly. Yeah. But in the end, I know your question. It's a good question. But I want to do one more thing. Yes. I know what he's want to ask. But it's a great question, but it's a bit off topic. So in a minute. And this, interestingly for us, this is what Bense talked about. We may be able to differentiate between these two populations, because these that are closer in to the supermassive black hole, they will have different phase when we see them due to gravitational wave emission. Okay, and then we calculated the rate, and the rate is sensitive to simply how many binaries are there. This is very trivial result. It is not sensitive to how you distribute the binaries around the supermassive black hole. It is not sensitive to so much to the mass that you choose for the binary, to the initial IMF that you use to the binary. It's mostly sensitive to how many binaries you have in a steady state configuration. And it's roughly comparable to the numbers that we heard before. And think about this. This is just inside 0.1 parsec and only very, very soft binaries. So there are all these other cool ideas that we heard about that should be added. All right, so we heard about how the supermassive black hole can merge stars, and then maybe they are G2-like stars, maybe they are young stars, and maybe the supermassive black hole can also merge black holes. But what else? I want to say something how the binaries are really confusing us when we look at the stellar disk. And this is something that Andrea said in the beginning of the day. So here is our, this is the theorist idea of how the stellar disk looks like. This is taken from Tal Alexander's latest review. And here is how I modeled it. And I need an observer, so I've put here an observer. And the observer, she looks at the, this is you, Andrea. And she looks at the stellar disk. And the thing is that, as Andrea said, that the disk membership and other properties are being based on only one kinematic measurement, usually. So if I have a binary here, and this is of course not to scale, that can actually change the way that I'll interpret what the disk properties are. And this is how it looks if I decide that every star is a binary, and I simply ignore the fact that they are binaries and try to see how the disk will look like. And this is because this is my input, so this is the velocity. So this is, I'm showing a velocity as a function of the semi-major axis around the supermassive black hole. My input velocity in blue is basically the velocity of the system around the supermassive black hole. And then the wobble that we have is in red. And you can see that the addition of them both is the gray. And basically what it means is that I get a broader distribution than what I actually started. And this is what I have for the fraction of the membership fraction per bin of a projected distance. So this is the fraction of stars that it's in the disk, in the red one, that per a projected distance. So here, very close to the black hole, this effect is very small, as you would expect, because the velocity around the supermassive black hole is larger. So this is it, and then it goes down because the membership that I will infer if I'm ignoring the fact that there are binaries there will go down simply because I didn't take into account they are there. Interestingly enough, if we look at what the observations are doing, they also seem to have the same trend. And that may be infer that we have binaries in the disk that we need to take into account. It also can cause for eccentricity to be higher. So I start with all the orbits on the circular orbits around the supermassive black hole, but the apparent eccentricity that I measure as an observer will be higher, just focus on the red one, because I infer those velocities wobble as an eccentricity. So to sum up, what I've showed you is that binaries can help us understand the young stars that shouldn't be there, the gas clouds that don't seem to be like clouds, the LIGO measurements, and they really confuses us when we're trying to understand the stellar disks. And that's it.